pa ako inaantok. I'm still lecturing, especially one of the phases of matter, which is gas. So, as I talked a while ago, and I discussed a while ago, we have two types of gases, the real gas and the ideal gas. So, they behaved exactly the opposite of each other. Something like, okay, in the real gas, it's a review that considers the molecular sizes and molecular attraction. Okay, and then this is equal to PV over nRT is equals to 1. Okay, P pressure, V volume, and then X number of moles per amount of substance, R is the universal gas constant, and T is the temperature in Kelvin equals to 1. Okay, like that, it obeys like that. P times V over nRT is equals to 1 is real gas. And then we employ the equation of van der Waals equation. Okay? Do you remember that one? Van der Waals equation. Okay, like that. Okay, so the pressure correction and the volume correction is equals to RT. Okay, and then the equation is more complicated compared to the ideal gas law or the general gas equation, something like that. Okay, and then now I'll be able to discuss, okay, what I have here, since I promised, okay, to discuss some topics because yesterday I stopped, okay, to continue that one. Okay, so I am going to talk about residual property. So residual property is the difference of the ideal gas and the real gas, or the ideal gas property and the real gas property. Okay, like that. So normally we have problem solvings on the ideal gas law. Okay, like that. Molar mass equals the molecular weight times the numbers of mole, and with that we can compute the mass. Okay, molar mass also mass over volume, and you can import to the ideal gas law also, you can get the mass of the monatomic gas. Okay, since we know that in the PVRT there is no mass, only number of moles. So we can derive by the molar mass and the density, something like that. Okay. Combined gas law is stated by Dmitry Mendeleev. Okay, Dmitry Mendeleev. Okay, so the Charles law, the Boyle's law, and the Gay-Lussac's law are being combined to achieve a formula: pressure 1, okay, times volume 1 over, okay, temperature 2 is equal, no, sorry, temperature 1 equals to pressure 2, okay, volume 2 over temperature 2. Okay, you don't have to write anymore because it will take time. Okay, again, P1 T1 over P1 V1 over T1 is equals to P2 V2 over T2. So we combine the Boyle's, the Charles, and the Gay-Lussac's. Okay, the Gay-Lussac's, by the way, was not mentioned yesterday, but that is pressure 1 over temperature 1 is equals to pressure 2 over T2. Okay, then the volume is constant. Okay, like that. Absolute zero. When you mean of absolute zero, that means 0 Kelvin or negative 273.15 degrees Celsius. So absolute zero is the lowest temperature, okay, at which all the particles movement stops of a gas. Okay. STP, meaning standard temperature, you can convert that also to Fahrenheit temperature to 0 degrees Celsius, and also the pressure can convert to kilopascal. 1 atmosphere, how many kilopascal? 111.35 kilopascals. I discussed yesterday, like that. And then it's G for the 7 psi, 716 energy, like that. Okay. Avogadro law. It's been discussed already that it is the volume divided by the number of moles or amount of substance is equals to the constant, something like that. So our constant will be the temperature and pressure. Avogadro. So yesterday I got a mistake. I told you that you should research also because that was only mistake knowledge. So actually I said that 6.023 times 10 to the negative 23, but actually that is positive. 6.023 times 10 to the 23, but it's not moles per molecule, but it is uh, molecule residue negative 1 or 1 over mole. Okay, so mole will be the denominator. Okay, something like that. It could be the atoms, the ions, the electrons, like that, and then the molecules. Okay, it depends on the problems, but the mole will be on the denominator. Then if you're going to raise it, the upper portion of the mole negative 1, something like that. Okay. So it's been discussed already. So R, universal gas constant, gas is equal to the product of the Boltzmann constant and the Avogadro constant. Since for Avogadro constant raised to the power 23, and of course, our Boltzmann constant is to be raised to negative 23 to cancel that out. Our value of R, capital R, or the UGC, universal gas constant, ideal gas constant, is don't have an exponent. Okay, it is 8.3145, something like that, joules per Kelvin mole, or stating that in terms of atmosphere, that is 0.08 2016, like that. 08, no, sorry, 0.08206, or rounded as 0.0821. Okay, letters, atmosphere, mole, Kelvin. So as you can see, that mole Kelvin should always be in the denominator. Okay, and then it could be in kilopascal, which is 8.314. 8.314 letters, kilopascal, mole, Kelvin. Something like that. Just something like that. Okay. So in energy, in terms of considering the kinetic energy, overall kinetic energy of the monatomic gas of gases, and the temperature, it will become E is equal to halves N RT. Small letter N, as I discussed a while ago, N is the number of moles and the amount of substance. Okay, so since you remember theory of relativity, okay, theory of relativity by Albert Einstein, there is also an equation of energy which is equals to mc squared, mass times the velocity raised to the power 2. C stands for the velocity or the speed of light in a vacuum, which is equal to 3 times 10 to the power 8 meter per second. Okay, if you try to equate that one, the two energy formula equation, okay, this theory of relativity by Albert Einstein is equal to the energy which is derived by statistical mechanics. Okay, so E is equal to 3 halves in RT, and then you can equate that one and you can compute the value. Okay, like this. Okay. This one, I'll show you. Okay. Ideal gas law considering the kinetic energy of a gas. Okay, and the temperature will be equal like this. Okay? Then you can come up with this equation. C stands for the speed of light, or the velocity of light, is equal to the square root 3 halves RT. Okay? And then you can substitute or plug in the values and you can get what is being required. Okay? Something like that. So this Albert Einstein theory of relativity will really usually come up in the examinations most of the times, because this is very common and familiar also in chemistry. Okay, like that. And it's even more familiar than the van der Waals equation. Okay, like that. Okay, van der Waals equation power 2 times the constant A, or the number of moles squared. Okay, plus open parentheses, and then plus open parentheses again by the volume fraction. Volume minus number of moles times the constant B, small letter B, and plus parentheses equals to MRT. Okay, so small letter A and small letter B are the constants. Okay, and then N again is the amount of substance, small letter N. Okay, V is the volume, something like that. It's very again, the same thing. That's the property. Okay, like that. So I write this a while ago in order for my discussion to be fast. Okay, like this. Okay. Energy is always joules. So the 1 calorie is equals to 4.124 joules. Okay, like that. Since joules is equals to Newton meter, okay, then Newton is equals to kilogram per kilogram meter second squared, something like that. Okay, then you can. And Planck's is sort of black body radiation or electromagnetic radiation. Okay, and then the other one is the Boltzmann entropy formula. Okay, this Boltzmann constant is related to the factors of Boltzmann entropy formula and the Planck's law, black body radiation. Okay, very deep na kalalim siya, di ba? Yung mga equations. But this Planck's law of black body radiation constant also is used there, which is the energy of the photon. Electromagnetic radiation, something like that. Okay, in which the value of Planck squared or something like that. Okay, the purpose of memorizing that one is really to emphasize quick discussion, but you can also refer that to the textbooks or any chemical engineer's handbook like this, or thermodynamics textbooks, but it will take time to scan something like that. Anyway, if you memorize it and then you found inconsistencies in the units, then you can adjust it. Okay, like that. Oh, this is gonna be the exact one. At least you have retention in your brain, retention constant, like that. That's all I am to memorize the basic formulas. Okay, the volume, the density, the pressure, the force, like that. And then that's still in high school. And then you go to college, you become a submanager. It's easier, a little bit easier to understand. It's really difficult. Very difficult. Chemical engineering is very difficult. Okay, because you are studying substances that you cannot see. You could just imagine something like that. For example, electrons, protons, and neutrons. You cannot even touch those electrons and protons. You cannot even see them like that compared to other engineering courses that we can see what they are doing. Okay? For example, machine, what they are doing. Industrial, you can see what they are doing. Okay? So in chemical engineering, you are just imagining. Shall I say one of the most difficult engineering courses? Okay. Okay. So, standard temperature and pressure also. I discussed it already. Standard temperature, pressure. If we mean standard temperature and pressure, the temperature is 0 degrees Celsius and the pressure is 1 atmosphere. And try to achieve and try to get other equivalent for Okay, because there are problems that need to problems that states that what is the blah 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 at standard temperature and pressure, and then no more given values. This is temperature and pressure that asking for given already. Okay, and you will be shocked and surprised. There's only one given, and you are asked for something, and the formula requires so many variables or so many properties because there are such theories and principles that are really memorized already, such as this STP, it's under temperature pressure. So the temperature is zero, like this, the pressure is already something like that. Okay, with a combination of compression factors. Okay. If you are listening now, try to scrutinize and examine those, topics that can make mistakes because I will issue an error or error code. What else? Boltzmann constant, 1.381 times 10 to the 22 already discussed, right? Molar mass already discussed also. Specific gas constant, what do you mean by that? Is equals to the universal gas constant, the ideal gas constant divided by the molar mass. Okay, this one. Asterisk is just to signify that it's not the ideal gas constant, but it's the specific gas constant. So specific gas constant, okay, the universal gas constant, the gas constant, the Boltzmann constant, okay, the Planck's constant, okay. What else? The Avogadro constant, like so many constant in solving equations in chemistry, right? What else? So many constants. Electrical charge constant, for 1.622 times 10 to the negative 19 column. Column talaga. So columns equal to electrical energy in a second in a given period of a current, 1 ampere. Okay, so column second. Electrical quantity, electrical energy, okay, that's being transported in a second in a given current or 1 ampere, so per second. Okay, so this is the charge. Electric charge. It is for the electrons, right? Charge. And who's discovered that one? I forgot. Who discovered one? It's Michael Faraday. I forgot. Within every corresponding laws, equations, and formulas, there are equivalent scientists who discovered and formulated that one. Okay. That's it. And now we go to the practice problems for ideal gas law. So I will be able to at least one example, right? Because there's no example. Okay. I think I'm gonna choose the that involves pipeline, so that there's a diameter, something like that. So we can inject the pressure is equals to force over area, and you can insert that to the PV and RT. Okay, but I could not find the problem regarding that. It's in a textbook. I think it's in the physical chemistry. FICAM, I don't know. I have to check it out. Okay. Where's that? Wait for a while. Okay. It's here. I think nothing. Okay. I write that one in a piece of paper, an example. It's good to have an example. Okay. I think in YouTube have examples in YouTube also. Okay. waiting if I... Yes, you get that from YouTube. Oh, I forgot that one. We'll try. Okay. Okay, we'll try in YouTube example. Ideal gas law. Maybe have only here. Sorry, it's here. Another phone. We'll try to see ideal gas law. So we'll type ideal gas law. Gas law problems, right? So that we can apply the theories I discussed. Okay. So this one. Put a sound. Okay. I will just take the problems like that. Okay, this one I will try this one. Ah, and then to big the screen. The pose, right? Okay, this one. Okay. 2.3 moles of helium gas. Helium gas, so monoatomic gas, right? Because ideal gas law is applicable for monoatomic gas, okay? And then at higher temperature and low pressure. See, low pressure 1.70, okay? 2.2 moles of helium gas are at a pressure of 1.70 atm or atmosphere, and the temperature is 41 degrees Celsius. What is the volume of the distribution only? Okay, so like this. Oh my god, this actual. Okay, so again, 2.3 moles of helium gas at a pressure of 1.17 atmosphere and the temperature is 41 degrees Celsius. What is the volume of the gas? So what is being required or being asked is the volume. Okay. Required volume. Okay. Like that. So the given is number of moles 2.3, then the pressure of 1.70 atmosphere, okay, and the temperature is 41 degrees Celsius, okay, like that. 2.3, pressure is 1.70, temperature 41 degrees Celsius. Then we will be able now to use what is the exact formula for this. Of course, we will use the ideal gas law for ideal gas equation. So E V N R. Okay, there's pressure, there's temperature, and then the volume is being required, and then the moles is 2.3, and we don't have the R yet, our ideal gas constant. Okay, and we have the temperature. So now we will scrutinize the units. For the pressure, our unit is written in, correct? For volume, which are required, okay, not yet. So this one, okay, and then number of moles is correct. R, not yet. We have to find out this one. Temperature is Celsius, so we need to convert it to Kelvin. Celsius plus 270. So 41 plus 27. Okay. Calculator here. 1 plus 70. 314. So find the R. So this is since our pressure is in atmosphere, we will use the liter atmosphere ideal gas constant. Okay. Actually, the R is not given, but you have to memorize it. Okay, or you have to look on the textbook. Okay, or anywhere you will find that one. So R will be 0 atmosphere. So we will just use as R. The value of R is 0.08206 liter atmosphere mole Kelvin. So it will add the other units here. And then we will simply plug in and we will get the volume. Okay. So like this. Solution. So EV and RT, get the value of V. So E, so E. So volume is equals to now. Okay, we have volume. It's equals to nRT over P. Now let's make this R to be the last to make it easier. We will multiply this directly to T. This is 314 Kelvin. Pressure in 1.78 atmosphere. And now we will multiply with R. Last, we make R last. Okay. 0.006 liter atmosphere. 1 Kelvin. This is 1. Now I plug in that one by one already here. Okay, we have number of moles to moles times this gas constant, that is the gas constant to be the last. Temperature is 314 degrees Kelvin, 314 Kelvin over pressure, which is 170 atmosphere. R is 1, 0.006 atmosphere, 1 Kelvin, and then cancels that out. Moles cancel. Okay, cancel. Kelvin cancel. ATM is cancel. What left is liter. Okay. 0.08. 33.98. Liters. The answer is 33.98. Okay. 33.8 liters of helium is needed. Okay. And let's check here if the answer is correct. Let's press forward. Okay. So the answer is 34 here. 33.98 liters. Okay, it's almost the same. Okay, only point something. But I checked, all are plug-in the same. Okay, so it's correct. It's only slight difference because he he round off what matters because the solution here in the YouTube, the 0.08206, he round off as 0.0821. Okay, this solution, but I don't round off, I have 0.08206. Maybe it matters in point something like that. Okay, it's correct. That's merely substitution. Okay, or plugging out. At least we give an example to that. Okay. So what time now? I must check it. Thank you so much for spending your time with me because I'm not sleepy yet. Okay. Thank you so much. God bless. Bye bye.